a tree of derivations. It's a set of processes and a set of pieces of information that show how the information is linked up and how it got from its original sources all the way down to the product that you're looking at. So aside from just generically tracing backwards and trying to figure out where did something come from, one of the cases we see a lot with government clients is various forms of intelligence corroboration. So you get into a lot of analytical situations where you have competing reports, whether it's the Haiti earthquake or whether it's a disease outbreak type of a scenario. You get a lot of pieces of information, and if you're hearing from 5 different places that there are some refugees who are trapped in a particular area, you need to know whether that is actually 5 independent reports that are corroborating one another, or whether that is in fact 5 different views of the same guy giving one person information. It happens all the time that, if I say, I want to report that there are these refugees in this location, and then I report it to another place, and then I report it to another place, that filters down, and an analyst sees 3 corroborated reports, but it's all the same source of information. Okay? That's a common use case that we see. Another one has to do with trust assessment and warning. Intrusion detection. If you're getting data through a complex sequence of events, when it gets crunched and down to you, if there is any vulnerability along the way or any methodological problem along the way, you can't necessarily trust the result. And so there come these situations where you have a sensor network gathering data. All of this raw data gets processed into a finished product. Now, someone who is manning the sensor network actually knows that the information is incorrect, but has no way of propagating that down to the consumer of the analytical product, if you follow that. Okay? So what we would say there is that the information producers and the consumers are decoupled from one another, because whoever is producing these sensor reports doesn't know who has the final analytic product, and vice versa. So if the guy who's running the sensors or who has the base data knows that something's wrong, the consumer of the end product won't be notified, which is a big problem in a lot of cases. So the objective behind most of this is establishing a graph that shows you how data was derived and allows you to do various types of trust assessments and warning functions. Now, trust assessments get very complicated. We'll give some more detailed examples of that in a little bit. But as I said, producers and consumers are usually decoupled. The right hand usually has no way of finding out what the left hand is doing. And so if you maintain this linkage and you sort of capture the graph of data derivations, it permits taint marking and propagation. So imagine that every single piece of information in an enterprise was like a blog that you could subscribe to. It was a source of information events. And then people could update that saying, well, this is now officially considered out of date, or this was based on faulty information, and that information flows down to the consumers who are subscribed to that information. Okay? So every information resource essentially becomes its own feed. So let me pause for a second. Any questions about this aspect here? Okay. Mission impact assessment is another area where we see a lot of stuff, a lot of interest in data provenance right now. Again, complex chain of infrastructure that calculates through to some kind of a mission result, whether we're going to drop a bomb on a target, whether we're going to do some analysis of a potential target, whether the IRS is going to go after somebody for tax evasion, whatever the case may be. Okay? The question then is, if something inside of this big infrastructure breaks, is that bad? What does it break? So if you have these provenance graphs, you can sort of trace forward and say, these things depend on these other things, and so therefore if this component breaks, then this product can no longer be generated. Okay, so this is a quick example of a concrete provenance graph. We're going to talk more about this one. A couple of things to notice. The rectangles are generally going to denote processes. So that is either a person or a piece of software that took some input and produced some output. Many-to-many mapping. It could take any number of things as inputs and produce any number of outputs, but it's a function, if you will. And the ovals and the circles, are essentially data. And so they might be any number of different kinds of data. It could be a single row in a database, it could be a file, it could be an analytical product, whatever it is, it's a piece of data. And so in general, if you had a complete provenance graph, and most of the time they're not, but if you had a complete provenance graph, you would have what we would call a beaded necklace, in that it would be strictly alternating boxes and circles, because everything produces some piece of output data, which is then the input to something else. Okay? And the last thing to keep in mind about provenance is that the graphs themselves can be nested. And so you can imagine us taking this entire graph and then black boxing it, and then calling the whole thing a process. And then that process is then linked inside of a larger graph. Okay? So you could think of this whole graph as a drill down of one particular process. Okay, so I've given you enough context, hopefully. And please just jump up, throw your hand up, ask questions as we're going along. So I've been doing this stuff since about 2009. And when we first built our first prototype on how to capture, store, query, report provenance, we used a mixture of MySQL and Postgres. Why did we do this? Well, we did it because it was simple and easy, and we had a lot of skill sets lying around. A lot of people knew how to do it. We had readily available tools like Hibernate. So we had these object relational mappers, and so ultimately everything needs to be a Java object somewhere along the line, and Hibernate gives us a way to store that inside of a relational table. Okay, done. Well, you know, relational databases can store anything, so why not graphs? So that's what we did. Essentially, like I'll spare you the gory details of the relational schema, but what it basically boiled down to was two tables. That's it. One table for provenance objects, that is the nodes in the graph, and then one table for provenance edges, that is the relationships in the graph. And so essentially what you had was a join relationship, so that if you wanted to put together the graph, you could join nodes, two nodes via relationships, and establish any arbitrary graph of arbitrary complexity. So yay, relational databases. All we have to do is discover the graph structure by joining the object table to the edge table. So it had a lot of nice things about it. I mean, one of the things was that relational databases, the way that they lay data out in memory, puts everything next to one another in the table, and they have really fantastic indexes. So if you wanted to look up an individual object by a property, say give me all objects where the name equals blah, 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 relational databases just can't be beat on queries like that because they've been optimized for 30 years to answer those kinds of queries fast. Okay? And they have really good performance on one-hop edges. So for example, in this particular graph, if you look at the red circle, Iris messaging dispatcher, if you want to know what's immediately upstream from Iris, the relational database just really does fantastic on that query. The cons is that as we started doing analysis over graphs, we very rapidly got to the point where we're not just answering these kinds of simple questions, we're doing graph traversals, and we're doing, and what we really wanted was declarative graph query. So how many people are familiar with the distinction between imperative and declarative graph query? Anybody? Okay, so very briefly, imperative graph query is sort of like the traversal framework that you see in Neo4j, and that's where you say, you actually specify how to traverse through the graph. And so you say, well, I want to do a depth first search, and I don't want to go any deeper than 4, and look at these branches first. Okay? And declarative query is where you don't specify how you want to traverse the graph, but you rather just say, these are the results that I want, give them back to me. I don't care how you traverse, I don't care what order, just give me stuff that matches these criteria. And that's really what Cypher is doing for us. Okay? So when you're in a relational database, writing SQL for a graph operation was very complex and performed very poorly. I've got an example query here, but if you wanted to do a depth first search over that relational structure that I specified on the last slide, it's pure pain. I mean, you can do it, but it's pure pain, and it performs very badly. And so in general, when you start wanting to do things with graphs, like graph traversal or declarative query, you get stuck with one of two options. Your first option is to write wizard level SQL. And what I mean by that, I'm going to show you in a second, but it's not something that a normal mortal who is used to using SQL can really pull off. Your other option is to push graph operations into your Java code, which is what I did for about 1.5 years. And so before I figured out a smarter way to do this, I was rewriting how to do a breadth-first search in Java over top of Hibernate with the graph in MySQL. And it got really cumbersome. And then so the project lead would come to me and she would say, well, all right, can you set up a query where we ask for nodes that are between 3 and 5 hops away that have these things? And I'm like, oh God, well that's 600 lines of Java. Give me a couple of days, we'll work it out. And that's the pain of doing it on top of a relational database. So this was a simple example I pulled off the net because the code that I had written once upon a time to do this was lost to the sands of time and probably horrible anyway. But in essence, like a example query that I use a lot is, find me a SQL query that finds all paths from nodes 1 to node 6 and orders the result by path length. So the solution on the right is a partial SQL solution, which involves you also having separate transact SQL methods that encapsulate some of the details that are within that. And so what you find yourself doing inside of SQL is re-implementing basic graph concepts in SQL and doing these really crazy recursive joins. So that's basically how you do a variable number of hops in a graph, is that you join one table to another, but you do it recursively to a certain depth. Okay? And all of those joins cost. Okay? So, all right, that's a part about relational databases. Now, as our application moved along, I'll show it to you in a little bit, or a part of the application, we found ourselves having to write a lot of what we called fitness widgets. So Provenance is this big graph, except most people don't really want the graph. What they want is some simple analytics over the graph. Okay? An example of one of these fitness widgets would be to say, show me the chain of custody. If I'm looking at a particular file, whose hands has it passed through and how many hops did that take, right? So in this particular case, the chain of custody was Air Expeditionary Wing to TBMCS, to Air Expeditionary Wing to TBMCS, back to them. So it's like back and forth inside of this loop. Now if you think about it, calculating the chain of custody for a piece of information is sort of like tracing a graph path and then saying who owned it at each hop. Okay? So the principal investigator of this project would come to me and she'd say, I want to do such and such, which was a completely reasonable thing. And I found myself, for each of these fitness widgets that we were building huge chunks of Java that performed very poorly and that were very brittle and very difficult to maintain. And the reason that this was happening is that because relational databases didn't support the concept of the graph, essentially all of the graph stuff was getting pushed into my application code and it wasn't happening in the database. All right? So I started talking to some graph nerds in the company. There's one guy who had done a lot of research in the 70s on graphs, and he said, well, there are such things as graph databases. Why don't you take a look at one of them? And that's about the time when I discovered Neo4j. The reason that I picked Neo4j as opposed to any other was, well, this was my shopping list. Okay. So what I really wanted was declarative graph query, not imperative traversal. When you specify how the traversal happens, you have to control a whole lot of fine level detail. And it's very difficult to optimize because you don't necessarily know whether going down this path first or this path first would result in faster execution time. And when the graphs get really big, you need to not be thinking about that every single time. So I wanted to be able to say, hey database, here's what I want. You figure out how to make that happen. Don't ask me to write a traversal engine over a graph to best figure out where my data is in this big mess. Okay? Now I know I needed a flexible schema too, so we had this basic schema for Provenance where we had a set of objects and a set of properties that were always going to be there. But we knew that when we deployed this software, we went into a lot of different environments, and then sometimes it was like a sensor fusion environment, and they cared about really detailed technical metadata about sensors. And then sometimes we were in an analysis environment where they cared about metadata about Word documents, because that's most of what they used. And so I wanted a flexible schema so that I could deploy my base schema and then extend it as necessary for these various domain ideas, and not have to reconfigure, say, a MySQL schema every single time for every deployment. Okay? And my other thing was that it has to play nice with Java, because enterprises trust Java, and let's say that I had picked something like Clojure, it wouldn't have mattered how good my code was. They would have stuck me behind so many requirements. You know, Clojure, that sounds new and crazy and risky. I needed to have something that I could say, well, okay, maybe Clojure is a bad example for this because you can deploy it as jars, but I needed to have a pile of jars. Okay, but Clojure is a bad example. All right.
OCaml.
OCaml. Pascal. Pascal. So if I had said, oh, you know, all of your problems will be solved with Haskell, I would have been laughed out the door. Not because Haskell is a bad language, but because of this enterprise supportability issue. Okay. So, you know, big reveal. I know you're shocked. I looked at my shopping list. I did a lot of research online about what my options were, talked to some people, and Neo4j was what resulted. So what I'm going to show you tonight, very briefly, and I mostly want to get to, you know, questions and discussion about all of this, is we have this research prototype that's out on GitHub right now called Plus, which is Provenance Linking and Understanding Sources. Now, when we use the software with our clients, a lot of times we're using it as an embedded API that gets built into a bigger system. The system that's out there on GitHub is kind of like a research prototype that lets you visualize this stuff, query it, work with it. A lot of times we wouldn't deploy that prototype just as it is, but it's to give people a flavor of what Provenance is and how it works and what you can do with it. A more typical deployment is somewhat custom in that we take the API that helps you capture Provenance in the first place, and then we build it into a distributed system so that as the system is running, it's actually capturing and logging this graph. Okay? And so we tried to set it up so that it's reasonably easy to run. If you clone it and run one command, hit a URL locally, you should be running it. Our uses of Plus. A lot of times we use it as a provider of information fitness widgets. So we'll go and we'll talk to the users and we'll say, what are the criteria that define data that you can trust for your mission? And so a user might say, well, I like stuff that comes from the Air Force because I know they've got really smart guys over there. And it can't be more than 6 months old, because if it is, I know it's going to be worthless. Okay? And it needs to have been processed through this particular system because it's what I consider to be the trustable system of record. And so those requirements basically get rolled into a graph query. So where we're saying, look at this particular item the user is interested in, look at everything back in the backwards provenance, and the backwards provenance must contain all of these criteria, otherwise the item is, quote, untrusted. The system doesn't define what constitutes trust, but it just sort of elicits from the user, what do you say is trustworthy, and then we'll compute for you that list of things across the information that we have available. So another big use of it is that it's a basic database for capture, query, and reporting, and so you already know what that database is. It has an API for building Provenance capture agents. Okay, so we tend to work a lot in the area of distributed systems, so you have a bunch of computers talking to each other over networks, through enterprise service buses, you name it, right? And so where the API comes in is that we tend to instrument these distributed environments so that when they pass messages through control points like enterprise service buses, the message gets logged, and we know where it came from, and we know where it's going, and we know what the message was, and then a whole bunch of message interactions like that forms the basis of building this larger graph. Okay? So, just a little aside here, the W3C has been working on a standard for Provenance for the last couple of years. And so they have, it's called ProvDM, Prov Data Model. Okay? And so it's all specified in OWL and RDF. So the group of people who are specifying the W3C standard are more academic focused. and they are focused primarily on hand-curated provenance sets. So the use cases that they're after have to do with things like e-journalism, where I want to write an article and then cite my sources and then cite where my sources came from. And the assumption there tends to be that the provenance graph is all manually captured and curated by a human being. And we tend to be more in a slightly different space where manually capturing and curating the provenance graph is not a feasible thing to do on an ongoing basis in a distributed system. So we're much more focused on more technical, sometimes lower fidelity provenance, but on a much bigger scale and across distributed systems. Okay? So if you Google around about provenance, you may run into the W3C Prov standard. It's relatively new, and just I would ask you to consider those differences in focus between hand-curated versus automatically captured.
So I looked at it a year and a half ago.
Uh-huh.
Where do you think Prov and the W3C would fall down in terms of the things that are capturing provenance on the kinds of data that you look at?
Well, so one of my first comments about Prov is it's very big compared to what we do. The model that we use is, I would describe it as a very small subset of what the W3C spec is, because the W3C spec allows you to say all kinds of powerful things that we don't think that most people are going to practically be able to capture. So for example, you can say this file was created by this software, which was delegated the authority to create it by data. Okay? And so that's powerful, and if you're going to hand curate your provenance, you could say those things, and you could exploit that data in many wonderful ways. But we would, our model of the world would say there's a file that was created by the software, we're done. Because what human delegated the software to run is not something that would probably be available at runtime. Okay? So I think one area where it falls down is its size. Another possible area where it falls down is that it's very oriented around semantic web concepts, and so they have specified an ontology, and they have in mind, I think, some reasoning use cases that in my work with my direct clients are not borne out by more realistic requirements. Okay? Now I don't doubt that they are real requirements in the sense that if you're doing hand-curated data sets and e-journalism, I think that they have some legitimate use cases. It's just that as I work with my clients and what they're interested in, I see that the W3C model has a bunch of stuff that they don't need and is missing some things that would be very important to them.
So the W3C model is covering the underlying JSON format that the data is stored in, or what is it, or the set of data that needs to be there in order for an object to be considered provenant? Or what?
Not the JSON part, but the data model part, yes.
Okay.
And so that data model is expressed abstractly in the standard, but then they also have an ontology for it, and then they also, actually come to think of it, the ontology has other expressions. They'll tell you how to encode that data as XML, as JSON, and as...
RDF.
Yeah, RDF.
Yeah.
Right.
Okay.
And here again, like, if you had a big provenance data interoperability problem where you needed to send somebody a provenance file and know that their tooling could understand it, then such a standard would be really useful because it would define what the correct way to interoperate would be.
Yeah.
I think the state of where provenance is right now is not quite there yet. So we would want to see a whole lot of implementations of different provenance systems keyed to specific requirements and the different file formats that they came up with before we would want to try to compare them all and say what format defines the intersection of requirements.
Yeah.
Does that make sense?
It does. I mean, it occurs to me I could see this being most useful probably in the area where it was intended, which is in kind of public domain knowledge, right? So what are facts in history, for instance, or what happened at such and such an event that is publicly known and needs to be exchanged or consumed by various systems. There I could see it making sense, but
absolutely.
I doubt for any specific organization for their internal systems, it would seem like a lot of overhead for potentially very little gain.
I think that's right. I mean, if you sort of adopt the semantic web viewpoint that people are going to publish these data sets and that they are going to annotate and curate the data sets online, then the way that they approached it makes a lot of sense. It's just that that's not the problem that most of my clients have.
Yeah, makes sense.
Okay. Yes?
Has anybody tried like reactive programming in this area? Like where you have data flows, like Excel, where if I change a cell, all the other cells that have functions attached to that, like it propagates those changes through. Because it seems like that would be like a really interesting solution for this type of stuff.
I know what you're talking about, but I'm not quite sure how it would apply in the case of, say, a distributed system where a sensor picks up a piece of data, that piece of information gets fired up to a web service, that web service transforms it into a different format, sends it over to another service, and on down the line. Now, there are a lot of workflow systems out there where they try to orchestrate these flows with basically higher level programming constructs where, you know, if you have a whole bunch of machines that have a whole bunch of APIs and services on them, then you can sort of program the distributed computer, if you will, using workflows. But that's about all I've seen there. I'm not sure how the reactive concept would apply here, but it does sound interesting. Does that, I mean, I don't feel like I'm not really answering the question, but I'm not sure what you mean.
Oh no, I was just wondering if you had like that had been tried, or because I know other things use it, but maybe they're for more of like an enclosed application. So if you change, like Excel's the most commonly known case where I have data in many sheets spread across many different things.
Yeah.
And when I change something in this cell over here, the reactive programming logic behind it propagates that change through the next cell, and then that triggers the next cell to change. So everything knows kind of its provenance of what it's depending on.
I follow you. I've seen that done with some workflow systems or something very similar to it anyway. Where it gets really tricky is where the systems start crossing boundaries of responsibility or ownership. So, you know, for example, you pull an RSS feed from Slashdot and then you do something else with it and then you send it on to somebody else. There's 3 different zones of control there, right? And you can't install code on Slashdot to do something when it gets pulled. And you can't install code on the target system to where you're pushing the data. And so you have to kind of manage bits and pieces of it here. And you don't necessarily have the ability to orchestrate every cell in the way that you would if it was Excel.
Okay.
Does that make sense? When it crosses a boundary of control and then suddenly this thing is completely outside the scope of your organization, it gets a lot trickier. And I mean, so a lot of the research that I'm kind of papering over has to do with how to capture provenance across those kinds of boundaries and how to get as much of a graph as possible and as well linked as possible, even when a lot of it is outside of your control and you can't necessarily run code on somebody else's machine. But if you think about it in some ways, like the provenance graphs are a special case of logging. Really what we're doing is, you know, logging system function. But instead of like really myopic logging, like let's say Apache logs what URL you hit and then what the response code was, we're trying to log the actions of a distributed system rather than one machine looking through a straw logging exactly what it's doing at this moment and nothing else. Okay, so on to a little bit more Neo4j stuff. A lot of our queries are not that hard, but this would be an example of something that we would do all of the time. I want to match a particular node with a particular identifier, and I want to grab any invocation, which is like a process that ran, that's between 1 and 5 hops away. Okay? I can't tell you, like, if you've worked in relational databases, this is pretty dumb and pretty simple from the Cypher perspective, but it's kind of a revelation if you're used to working in a relational database, because this is this 3 lines up here at the top is one of the things that I would otherwise be doing crazy acrobatics in SQL to do. All right? And then, you know, another simple question would be like, does this item flow into any common operating picture? And so I might say, well, I know what the common operating picture nodes are. Are there any of those downstream? Okay, simple directional queries. Variable length paths are all over the place for us. Another one might be, you know, how many hops away is this particular thing, so the length of a particular path, and how many different data items from TBMCS contribute to this node. And so this might be a slightly more complicated one, but we might say, the user might specify, I only trust stuff that came from TBMCS, and so in order to answer whether or not this is good for you, I need to know how many things from TBMCS flowed into this, and then this is how I would answer that query. Okay? Okay, so like I said at the very beginning, I use all databases, and I'm not a big believer in the free lunch. So in order to give you some balance, hopefully some honesty, I wanted to talk a little bit about what you give up. So I want to very briefly introduce the concept of natural indexing in a database. Okay, so in a relational database, I think I might have mentioned this briefly a little while ago. Inside of the memory in the computer, row number 2 is typically right next to row number 1 on actual storage. And this means that if the kind of query that you're going to run is going to basically scan through the rows and then grab some of them, that tends to perform really well in a relational database because the data is already, quote, naturally indexed or laid out in memory in such a way to facilitate that query very, very quickly. It's not like that in Neo4j. Neo4j tends to be naturally indexed by relationships. And so when you read online in the documentation, you can traverse a whole lot of relationships really fast. And this is why. This is Neo's unfair advantage. So you can index by label and by properties, but from what I've found with a lot of experimentation, if all you care about is label and property scans, they're never going to be as performant as RDBMSs for certain kinds of bulk queries. Okay? Now, you know, you have to make a decision for any application with the fullness of all of your requirements and not just some. No matter what database you pick, it's going to be really great in some things and not so great in others. But the reason I'm presenting this is to try to get to an understanding of what are the real differentiators between graph databases and relational databases so that you can make a more informed decision when it comes time to build that next app. Right? So let's be really unfair for just a moment. And how could I make Neo4j look really bad? Okay, well, I did it when I wanted to generate RSS feeds. Okay, so now this is a little bit unfair in that some of my original code was written against 1.9, and Neo has come a long way since 1.9, let me tell you. Okay, but this was one of the original queries that I was using, and so basically what I wanted to say was, show me stuff that was created today where its type is data. And I'd probably reformulate this query a little bit differently nowadays. But if you think about this, this is scanning just about every single node in the entire graph and checking for certain properties with certain values. Okay? That's the kind of query where a relational database is just fundamentally set up to win, and a graph is not. Now, I'm more than happy living with the trade-offs that I got because you saw all those variable length path queries that I got, and that's where the real work of my application is. But this is one of the trade-offs. So what we found with some experimentation is that there's 3 kinds of queries that end up being really bad news. One is the fishing expedition. That is, if you're not starting from anywhere in the graph, when you're just doing sort of like a bulk scan for any kind of a pattern anywhere, those tend to not be as good. Generic queries that don't apply to any particular label or index subset, you know, where you're saying match n where, etc., etc., those tend to be not as good. And the table anti-pattern. This is, for people who are migrating from relational databases, the table anti-pattern, we see this happening a lot inside of my company, is in a relational database, usually you'll give something an ID and then you'll link to something by a foreign ID, foreign key, rather. Okay? The table anti-pattern, what I mean by that is when people store the IDs of other stuff that they want to associate with nodes in the nodes. Okay? So that rather than traversing relationships, they look up the node as a property and then go looking for a node that has that property value. Does that make sense? Okay? So if you treat nodes like they're tables, oh God, it's awful. I mean, so along those lines, how to think in graphs. Let's take a simple example, like let's say I want to get all relationships that are in a particular workflow, in a Provenance workflow. This is sort of the the table way of thinking about it. Well, I have a workflow node, and I have a relationship that's tagged with workflow equals 1, workflow equals 1, and then I'm going to write a query, and I'm going to say, look through all of my relationships, and find the ones where the workflow ID equals 1, and then, bam, we've got our workflow relationships. I've seen a lot of examples like this inside, and that's usually like a relational database guy who is trying to use a graph database like a relational database. And this might be a slightly different way of going about it, where you have a workflow that points to its members, and then you just traverse straight to them, and then you have your members. And notice that instead of doing a bulk scan over every single relationship under the sun, instead we're just starting in one place and then navigating to straight where we want to go. And if you buy that Neo4j is indexed by its relationships, then you can see why the one on the right is gonna be way, way, way better. We're coming to the end, and I want to hear your questions and talk more about this. A couple of other observations on graphs, good and bad. This first one, we haven't run into this that much, but I bring it up because I'm interested in research. Partitioning and sharding is very difficult, and so in Neo4j and in several other graph databases, you'll see that they have these high availability setups where you can take a big graph and you can copy it onto more than one database, and then the high availability arrangement is such that the graph isn't huge, but you've duplicated it, so access to it is really, really fast. Okay? But if the graph gets so big that it can't fit on any one machine, it starts to get to be trouble. Now, if this were a relational database, we could do either horizontal or vertical partitioning, which is to say that if I had a table with 100 billion records in it, I could put 500 million on one machine, 500 million on the other, and I could make it perform reasonably well. Graphs don't work like that. So partitioning and sharding is kind of trouble, and it's subject to research. Most of the stuff that I've seen done are custom solutions where somebody happened to know a whole lot about their graph structure and they partitioned it in a really brilliant way, not necessarily with a whole lot of help from the software. So other graph databases that I've seen tend to kind of hide this, or they make other compromises to get around it. But it's a really hard problem. I mean, for computer science researchers, it's a hard problem. Not as in Neo4j is lacking the right library, it's that it's really a wicked hard problem. And so what we see is that it can presently scale to billions of nodes per machine and traverse thousands of relationships very quickly. I'd love to hear from like Neotechnology if anybody has ever done hundreds of billions of nodes on a single machine. I mean, I infer from the documentation that that's not wise to try. This is not a problem that I have run into yet, but it's something that I'm a little concerned about on the horizon. But then again, I'm also kind of stuck. I don't exactly know what to expect out of any software package here, given how hard of a problem it is. A good thing is the natural mapping from object-oriented class hierarchies into graph databases. So there's this thing that computer scientists talk about called the object-table impedance mismatch. And that is when you go to save a Java object into a table, well, an object isn't a table, there are differences, and so you have to manage joins and all kinds of other complexity. That's a lot easier with the graph database because objects in memory, Java objects in memory are essentially a graph, so it maps much more cleanly onto how to save a bunch of stuff in memory. Graph performance tuning, this is kind of a mixed item. It's a new thing to a lot of operations people and sysadmins. And so you get this situation where Oracle has a little bit of an unfair advantage because Oracle sysadmins who know how to tune systems are a dime a dozen, and they're really good at what they do. And there aren't that many people out there who know how to optimize performance on a Neo4j database. And so just the other day on Stack Overflow and on some of these Google groups, we were talking about how version 2.2 is going to have a cost-based planner instead of a rule-based. Anybody heard about that? Yes? Okay. I have great hopes for that. That sounds like it's going to be awesome. I'm glad that they're doing that. You know? But it's like we're trying to get better documentation and better guidance for how do you optimize this stuff so that over time people get more familiar with how to use graphs and you have less of this table anti-pattern thing going on. Because any database can do really well, but you have to use it in its area of strength and avoid it in its area of weakness. Otherwise, you get a false impression of what's really going on here. Okay? So that's about it. I have a lot of extra backup materials. I can show you, if the network is working, a little bit of what this looks like. Let's see if it works. All right, so this is actually what a Provenance graph inside of a running demo looks like. So you basically have this graph. Whoa, what happened? Plugged in. Power is. What gives?
Sounds like you probably disconnected or hit a button.
I didn't hit a button here. Let's see.
There we go.
Okay. Ooh, man, resolution. Okay, this would be an example of a provenance graph. So we have a set of RESTful services that provide provenance primitives over top of Neo4j. So behind the scenes is Neo4j, but we're not using the server's RESTful services here. You can do various kinds of visualization and clustering and configure how it is that you want to spider out and generate the graph. There are both provenance edges and non-provenance edges, so you can assert relationships between items that are not provenance, but you could say, like a user could come in and annotate and say this thing is the same as that thing. And you can control how it spiders out and so on. In general, we are organized by workflows, invocations, and data items. And so workflows are just those black boxes, big groupings of graphs where you might have a produce analysis report workflow. And you can imagine that that workflow was run Tuesday at 9 a.m. and it was also run again Wednesday at 9 a.m. And so those would be two separate workflows. Okay? An interface for querying through this, and at the bottom it gives you sort of a sense of what some of the fitness widgets or trust assessment stuff is. Inside of assessment, we have this kind of a demo thing where it's a stoplight interface. So let's say that we were to click on okay, GCC SI3. So this is a simple UI that we use for demos to show how to stack trust assessments. So essentially, we have term finders, taint finders, bad term finders, and a couple of other things there. And the user essentially says, I only trust stuff that is less than this amount old, has this in the backwards provenance, and so they express that, and then each criteria that they put in triggers a stoplight, right? So the stoplight's green if we found what you're looking for and that's a good thing. It's yellow if we don't have information one way or the other, we really can't say. And it's red if you're looking for this bad thing and I'm telling you it's there. And so it essentially then rolls up via a set of configurable rules inside of the tool so that if you have 3 greens, a yellow, and a red, you can define a trust policy that says, oh, okay, well, 3 greens, a yellow, and a red for this user in this case is a green. And other users might say, if there's any red, it's red. Okay? So these types of widgets here then get embedded inside of other applications, and they're driven by the database and by the API, so that as you're looking at something in a database, this little widget is beside you, and it has your canned trust query plugged into it that's running against the provenance, so that when you're looking at a particular document, you say, this checks out or this doesn't check out, depending on what the case may be. And so inside of this demo, you see it as this little window at the bottom of this graph visualization thing. But one of the lessons that we learned early on is that almost nobody really wants to see the graph. What they want is they want a question answered that requires the graph to answer. So, any questions? Yeah.
You almost completely answered my question, but So it was around your schema for so
Yeah.
to what degree things are hard coded, and to what degree can things be like, you know, comment fields, or, you know, obviously anything that you want to query and have automated has to be a schema element that you knew about ahead of time. And so I guess what I'm asking is, how do you kind of like strike that balance between agility and automatability?
Automability?
For lack of a better term.
So we have a published model that is kind of like the bare minimum. So it's not the case that you start with nothing and then you only add domain-specific stuff. It's that all provenance objects have a base set of things that are guaranteed. Like they're going to have a label, they're going to have a created date, they're going to have an owner, they're going to have privileges associated with who can see them, stuff like that, right? And then domain extensions come from that. And so there's a basic set of queries that you can run against everything because there's a basic schema that's always guaranteed, right?
Okay.
And then as you layer on schema concepts that are domain specific, we would then develop, like a lot of these fitness widgets, they really boil down to a Cypher query being run and then displaying the results of a Cypher query in a window. That's really all it is, okay? But we haven't, I can't say that we have that structured of a way of managing the differences between the domains because they're so different. But one of the things that we've been thinking about lately that's going to probably get promoted into the main model, that seems to be, like, it was not in our main model, but it's this recurring concept across all the subdomains we've been working in, is the idea of content hashes, or what we would call content-bound identifiers. A lot of times when we're tracing data through systems, we're going to take like an MD5 sum, or like a SHA-256, something like that. And the purpose of doing that is so that if we see the file in the future, we can know whether we already have a provenance log of it, okay? So if you send me a file in email and I take the MD5 sum, I can look up the sum in the database and say, oh, I know who produced that, and then link it in, as opposed to saying, oh, this is this new file I've never seen before, right? So that kind of content-bound identifier turned out to be useful in so many different domains, and it's probably going to get promoted into the model. Now, there are technical specifics that are never getting promoted into the model, like the details of like standard metadata that you would find associated with an Office document turns out to be useful in a bunch of subdomains, but it's probably not really provenance. Like who's the publisher of something, or what are the keywords for a particular document, right? It's kind of a trade-off. Some of the domains we worked in are so radically different from one another, we don't have much better of an approach than to say base model plus extensions plus an easy way to write add-on queries against your extensions. But that's how it works generally. Does that answer the question?
Yeah, to a degree, yeah. I guess, do users have an interest in like, run my widget, but then, you know, give me something that a computer can't read, but that a human can read? Like, you have like comment fields or something to the effect where, like in the field, people can kind of like tack stuff on without having to update Cypher queries and stuff like that to make use of it?
That a computer can read that a human can't
No,
read.
the other way around.
That a human can read. I would say that by far the majority is stuff that the human is reading, not that the computer is reading. So because we're primarily in the business of trust assessment, and that's a human thing that's mostly getting decided, that's what the stoplights are about, right? You tell me what you trust, and I'll just compute whether it's red, yellow, and green for you. You know what I mean? But, you know, of course I can make a stoplight machine processable data, but nobody has a use for that so far. They want to see the stoplight and know that their criteria are satisfied. Because usually the case that you're in is that the reason I care about this stuff is I have some piece of information and I'm about to take a consequential decision on the basis of this information. And so it's usually not a machine that is saying, before you can pass through this gate, you must meet a trust criteria. It's a human who's saying, I'm about to spend $1 million on something. So we need to be able to give them a green light. Like in quite in a literal sense, it's actually a green light. But then be able to back that up and say, it's green because you said you wanted X, Y, and Z, and I can prove that X, Y, and Z all exist.
Yeah, that's good, thanks.
Yeah?
Just probably a really minor question. On your graph, you're representing two-way relationships, right? But you said that in general you want to be reading this temporally, kind of left to right. So I'm just curious, like, are you know, the relationships between these nodes, do they really, right?
Right, so in this case, this is a provenance. The other thing that I was showing a second ago was a provenance graph. That was a picture of the schema in the database.
Oh, okay.
But
right.
This is a provenance graph, and the relationships are never two-way. They're always directed, and like, as you said, it flows left to right. So you can take it to the bank that this happened before that. So one of the interesting bits about provenance is that you can think of it as like a recording of the causality. And so think about this. If you accept that this caused this, is it ever possible that there's a cycle in this graph? No. Now, practically speaking, if your software is not set up correctly, it's possible to end up logging a cycle, but that doesn't mean that that's reality. It means you made a mistake somewhere, because effects can't precede causes. Now, this other thing, so the question was about our schema, and so I just have this other neat little tool I put out on GitHub a while ago. Inside of my company, we have a lot of Neo4j databases that get developed, and you get this zip file, and you're like, what the hell is this? What's in this thing? And there's this little schema tool we developed that will generate documentation for a database, if you will, and it'll say these kinds of labels exist and these kinds of relationships, and this kind of label links to this kind of thing. And so we use it as a way of generating schema documentation for a database. And so this is the schema documentation for my provenance database. Namely, there are these nodes that have a label provenance, and they can be related to other provenance nodes via a generated or triggered or contributed edge. That's what that graph is saying. And so provenance objects are controlled by privileged class nodes. Privileged class nodes have a domination relationship between them, so they form a lattice of privileges, if you will. Okay? And so, you know, essentially this is basically saying, if you look at this schema bit right here, it's saying that provenance objects are at the heart of our system. Big surprise, right? And they can be related to one another by all these different kinds of relationships, and then there's this security access control stuff over there. And so, you know, if you scroll down, this is just like, it shows you about our indexes and constraints that we use on the database. It's just documentation for our database. Yes?
Have you ever tried to take advantage of the strengths of both relational and graph databases in the same application, where you have this massive quantity of tabular data, but you need to do some relationship analysis?
Yes, that's a really fantastic question. So if you hang out with the database nerds at my company, some of them might say that, okay, you got this, am I really going to say this word, NoSQL? I guess I am going to. I mean, it's a lump concept for a lot of different stuff, right? So you have all of these different kinds of databases. You've got the MongoDBs, and you've got the like Redis. Anybody use Redis? That's a pretty cool one, right? It has a really cool niche. Now, me personally, I think the niche is fairly narrow, but in that niche, it's pretty awesome. Okay. And so it's tempting to think that with all these different database choices, if you had a mature understanding of the pros and cons of each, then maybe you could build a hybrid system where you needed graphs and you needed relations, and you used each in its area of strengths, and then knitted them together. Great concept. I'll tell you, practically speaking, I run into a lot of problems with this because you have to integrate the two, and you have to keep the data synchronized between them. So for example, if you're going to have a graph that stores a bunch of relationships, you're going to have to sync which node ID corresponds to which primary key ID in the table, right? Now that's effort and pain and integration, right? If your problem is big enough and your performance requirements are strict enough, maybe it's worth that pain. Okay, most systems that I've worked on, it has been easier to deal with a performance downside on this query or that query in exchange for a substantial amount of simplicity by only using one. So it's a balance, right? I'd say that that's a possibility and could be a good idea if your performance requirements are really intense. But it's a lot of overhead to manage two constructs and then the integration points between them.
You know, one of the reasons I was thinking of that is if I have a really well-established database and I want to do a little interactive research with it, using graphs, say, for example, that was one of the reasons. Not necessarily because I want them to be permanently integrated, or maybe only occasionally integrated, you know, instead of in a production mode. But it's interesting. So you're saying the sweet spot is a little more narrow than I was possibly imagining.
The sweet spot for what?
Of combining.
Yes, because I think that, like, in principle, combining them is a really great idea, but the pain involved with managing the integration is more than people think. So I think it is still possibly a good idea, just not in most cases.
Okay, so the next question is, how do we make that simpler? And the other question I wanted to ask, I have one more question. The other question is, when you said, you know, in a workflow mode, nothing ever travels back. You never have a cycle. You never have a
right.
But in the real world, cycles do exist, and sometimes information flows in cycles, and sometimes it causes positive feedback loops and other such things that occur in the real world. Like, for example, if you were thinking about, let's say, a microeconomy or something that you were looking at. Have you ever thought about that?
A lot. I think we solve this with a neat assumption about the temporal aspect of data. So,
okay, yeah.
First of all, I don't think you can give me an example of a self-generating file, which would be a true loop. So a file which creates itself. All right. Even if you had, say, source code that printed itself, it would be the execution of the program that produced the source code, not the source code itself, if you follow. All right. Now, if you had an example where a particular file was chasing itself around in a loop, then the way that we would cut through that and say there's still no loop there is that there is a difference between the data file at time 1 and the data file at time 2.
Well, yeah,
those are two different data files.
Time is always a way of straightening it out.
Yeah.
Linear.
But I mean, you know, if you think about it, it would not make sense to say that a file produced tomorrow influenced a file produced yesterday. It should not be possible to express that. And so that's like one of the constraints we have on our graph, is that we try to make it hard for you to say that, because we don't think that that could ever be valid data.
What about something like a future event that you know is going to happen but hasn't actually?
Well then, okay, so like I said, this is like distributed systems logging. So in the example of a hypothetical future event, it's not provenance yet, it hasn't happened. When it happens, we will observe that it happens and then log that it did. But if it's a future event, it's not provenance. Any other questions? Yeah?
Yeah, earlier you mentioned that you can take a whole bunch of nodes and relationships and then roll them up into one node.
Yeah.
How do you do that?
Well, I don't have a nifty UI demo for you on that particular point, but essentially, a lot of times we are instrumenting workflow systems, and the workflow system provides that for you in that the workflow module triggers this module, and then you can dive into that module and say that there's like extra complexity underneath of that. So sometimes the environment sort of specifies for us what the black boxes are that are useful. Other times the users might want to say, this whole chunk of stuff, I don't want to see the details, I just want to call it this block, right? None of that is done automatically. Like, you can't have software that looks at the graph and then abstracts it and decides where to draw the black boxes. But if the users can tell you where the black boxes apply, then actually capturing that as data is not that complicated. In essence, so if you were to look at this provenance graph here, okay, we said boxes are processes. This black boxing that we're talking about, imagine that this box was a workflow instead of a process, okay? Then we would have a little UI control element maybe that you would click on this and then click a button, and then the rest of the graph would disappear, but you would drill into it, if that makes sense. But as I said, like most of the people who we're working with are not actually looking. I show you guys the graph visualization because this is a graph group. And so I can show you a bunch of nodes and edges, hopefully without scaring you off. But the average user doesn't want to see this. And in fact, as graph visualizations go, one of the things I'm finding over time is that when the number of things on the screen gets beyond, say, anywhere in the 7 to 10 range, users very rapidly tune out because it's too much complexity, right? And so we put a lot of effort early on into trying to tune the visualization. So if you go to the Neo4j server and you query for some data, it gives you this force-directed sort of spring layout kind of deal, all right? But there's no temporal element there. I mean, how could there be? They don't necessarily know that your data has a temporal aspect to it. So we always lay it out left to right, and you'll see that we sort of lay it in tiers, right? So you'll notice that these inputs to this are all in a line and flow into it, and they're not like way over here somewhere, right? And then we do various kinds of clustering. So for example, if we know that all of this stuff is owned by the Army, then there's a clustering way that you can say, draw a circle that says Army and say it has 3 things in it, and then say Army flows to Air Force, flows to Navy, or whatever the case may be. And so those are like graph visualizations that are specific to what the data of provenance is that you couldn't do in a general graph visualization interface because you wouldn't necessarily have the data to make that apply. Yeah?
With this model, do you get it all into like remediation, that something shows up red, what it would take to get back to green? What extra data you might need to get from some source that would fix it and build, I don't know, some sort of state machine of how you would transition from your current bad state to a good state, or what would cause that to go back to bad state?
No, we can't do that. What we can do is, if your trust criteria is composed of, say, 4 facets, has to be less than 6 weeks old, has to come from the Army, so on and so forth. If you have a red stoplight, we can tell you which facet failed. Okay, so in some ways you could say, well, the reason this failed is because it didn't come from the Army. So if it had, then you'd be green. You can do it in that way, right? Now, one of the holy grails of provenance research that, to be perfectly honest, we gave up on a long time ago was the idea that if you capture enough information about a workflow, then you could replay it, right? So you could capture, like, this went into this. Imagine a simple functional composition, a function, like converting a temperature from Fahrenheit to Celsius. There's a simple math formula. And so you can imagine that if I captured all the input values and I captured all the transformations and they were pure functions, then at any point in the future I could replay that. Because I had the provenance, not only did I know where it came from, but I could reproduce the result. Okay? From my view, when we get into the real world, nothing interesting is a pure function. They all have side effects. And a lot of this stuff happens across zones of control where I can't necessarily look into and really know how that computation happened. So in this graph, you'll see, for example, a GCCS I3, right? And so it did a bunch of complicated stuff. And I know that something happened there, but I don't know exactly what happened there, right? At some level, you always run into these black boxes where what you're telling the user is there was a computation that happened and it produced a result, but I don't know what the computation was. And for that reason, our ability to give people remediation advice tends to be very limited because we can tell you how it happened, but we don't know exactly what the implementation was, if that makes sense. Yes?
How do you deal with, you said you had your basic data entities for provenance, and then you would build on the domain-specific ones. But how does that have to be frozen before you start doing this? Because what happens if you're in production and then there's like 2 or 3 more provenance elements that they want to add very early on? I know you have a temporal aspect, but how do you practically propagate them?
Yeah. Well, so in one sense, one of the nice things about Neo4j is that you have this property store, right? And at some level, every node is a key value store. So you can decide tomorrow that you want 5 new properties, and my code in Neo4j handles that no problem. All right? Now, there's a separate issue of, if you decide halfway through that you want to capture these extra attributes, of course, only some nodes have them, not all of them, right? So if you want to query on those attributes, you're only going to be getting stuff after the cutover point, not everything in your database, right? So that's sort of like there's a very big general schema migration problem that all databases have. So like, how do you change the model of the database as it rolls down the road? That's a very tough problem, and there's a lot of good stuff that's been done there and good approaches, but I don't know that stuff is really fundamentally different with Neo4j than with any other database. Is that you usually want to pick some kind of an information model and then stick with it. And then everybody ends up having to change their information model. Managing that change is hard, whether you're in graph or tables or whatever.
I just don't know if you can use Provenance to track that change.
Yeah.
Or flag it that something has happened.
Oh.
You know, using the Provenance information.
Yeah. Do you mean, well, so you can use Provenance on anything, so you could talk about the provenance of a database schema over time if you wanted to. But we try not to get too meta, right? I mean, so there's the provenance of the provenance database, right? So all of this information came from somewhere, but that's a little too meta. Any other questions? Well, thanks a lot for your attention. I know that this is, at times, heavy sledding. I mean, something I've geeked out about for the last couple of years, but thanks for sharing it with me. And if you have any other questions about Neo4j or Provenance stuff, stick around, hang out a little bit. There's more pizza over there. You guys are not going to let this go to waste, are you? Thanks again.
Cool.
Yeah.